I just added a quick link here for AP testing information on the home page there, and it's really just this document that was sent to me, and it should have been sent out to you guys as well, but it's a place for you guys to find it if searching through your email is a little tough to find things sometimes. All right, so this is our AP exam ordering and testing information for 2020-2021. There's your steps to complete. We've talked about these things. The last deadline here is AP exam fee payments. All right, this is the website that you need to go to pay for the AP exam. And then here's a little more of a breakdown for the steps. Please make sure that you have checked to see if you qualify for student benefit waiver for testing. You can do this at this website here. Have your parent or guardian fill out this survey. You need to apply it by the 25th, in 5 days, to allow your application to be processed in time to receive your discount code. Student must still complete the online payment process using discount code, okay? Exams ordered after November 13th will be charged a $40 late fee. Don't get charged a late fee. There is no cancellation fee for exams this year. However, this is no refund of fee. There is no refund of fees if students cancel their exam or choose not to test. All right. So again, this is just the information. It is also in this manual if you need that. All right, I just wanted to make a quick, easy place for you guys to find that. So it's on a link on the home page. Yeah. So there's that. As far as our module for this week, it is under construction. I can publish that, and we can publish that. All right, so the discussion boards should now be available. I didn't want to release them yesterday because I didn't want to add anything for you guys to do. I wanted you to just be able to work on the things that were already there. I have not completed the check your understanding for this week, so that is not going to be available yet. It should be available by tomorrow. All right. I think there's just some issues with Microsoft this morning. Yeah, my computer's kind of being a little punk right now too, so sorry, Daniela. Don't worry about it. Remember, the class will be recorded if you're not able to make it work right now. All right, so let's look at what we're doing today. All right, so it is Tuesday, October 20th, 2020. We're going to be completing section 2.1 today about describing location and distribution with percentile and z-score. There's just a little bit more that we need to talk about having to do with those things, and we'll look at some examples, and that'll be it. And then on Thursday, we'll jump into the normal distribution and density curves and things of that nature. It should be very exciting. All right, so as a review, a percentile, right? A percentile tells you the percent of observations less than the observation being considered. Okay, and an observation is just a value in our set, or value in our data set. We can call those observations. All right, so our percentile tells you in percent of observations less than the observation being considered. For example, if you scored a 75 on a test and you're in the 95th percentile, then you scored better than 95% of the other students who took the test. That's how the percentiles work. All right. This also means that 5% of the students who took the test scored the same as you or higher. All right. If 95% are all strictly less than, that means 5% are equal to or greater than. You need to have that equal to part somewhere. And it goes along with that other 5%. All right, standardized score or z-score was also introduced in our last week. Standardized score describes how many standard deviations of value is from the mean. It's a way to kind of like reorganize our data based on the distance from the mean. A z-score is positive if the value is greater than the mean, right? Or if it's to the right of the mean in the distribution. Right? A z-score is negative if the value is less than the mean, to the left of the mean in the distribution. So we can have positive or negative z-scores, and they tell us whether a value is greater than the mean or less than the mean, and how many standard deviations it is away from the mean. You can standardize a score with the following formula, right? Z equals x minus x bar divided by s sub x, right? Where these all have things that they actually are, right? Z is the name of the standardized score, right? X is the observation. X bar is the mean of the sample. And S sub x is the standard deviation. Of the sample. Right. And we have to have this sample, right, saying that this is of the sample, unless we're told that this is for the population, in which case we would use different notation implying or indicating that we have the mean for the entire population and the standard deviation for the entire population, in which case we would use a different notation. Typically, like I said, unless you're told that you have the values for an entire population, you will use this notation implying that it's for a sample. Okay. Right. So we can also compare data using our z-scores. That's one of the values of having a standardized score, is it can allow us to compare things based on the z-score. Right. So here we have an example. A student scored an 86 on a first test and an 82 on a second test. The mean for the first test was 80 with a standard deviation of 6.07. The mean of the second test was 76 with a standard deviation of 4. Right, so we've got a bunch of different data going on here. We have our two scores, right? We have the 86 and then the 82. We've got the mean of 80 on the first test with a standard deviation of 6.07. The mean for the second, standard deviation of 4. All right. On which test did the student perform better on relative to the class? So we can just look at the score and say, well, hey, they did better on the first test because they got an 86, and on the second they got an 82. Right? If these were both out of 100, obviously she did better on the first test. But if we're comparing to the rest of the class, when we want to say, okay, relative to the class, which test did the student perform better on? We can use the z-score to see how she did compared to the class. All right, so we're going to look at these scores. We'll use the first one. Oh, not the highlighter. I want the pen. All right, so if we're looking at our results here for the first test, right, we can have a z-score that will be 86 minus 80 divided by 6.07. And we'll use our trusty calculator. -86 minus 80 minus 7. And that gives us a 0.99 for the z-score as an approximation here. I'm rounding the decimals. All right, so our z-score on the first test is 0.99. Get our second test. All right, second. We got our second test. And that's going to give us a z-score of 82 minus 76 divided by 4. We'll get back to our trusty calculator. And this gives us a z-score of 1.5. All right. So then, based on our z-scores, which test did the student do better on? The first test or the second test? In other words, which test did the student have a larger z-score? Again, on the first test, we did 0.99, second test for 1.5. So we're about 1 standard deviation away from the mean for the first test, but 1.5 standard deviations away from the mean in the positive direction for both on the second test. So relative to the class, the student performed better on the second test. Right? And that's based on the fact that the student, relative to the mean, right, on the standard deviation is farther to the right, has a more positive score compared to the mean or the average of the class. Okay. What questions do you have? Okay. So, again, our standardized score or z-score can allow us to compare things that aren't always comparable, right? Like the two tests were different, they were on different content, right? And the scores were different for the class. All right, so the one measure is just the raw score, 86 and 82, but another measure of how well the student did is also how they did compared to the rest of the class. Okay. All right, can you raise your hand if you need another moment to write any of this down? Okay. So next, we're going to look at transforming in data. Right? What we just did with calculating a z-score is actually one way of transforming data. We're taking it from one unit of measure, which could have, in our example, was test scores, percentages, just a raw score, into how far away that score is from the mean. That's a different unit of measure. And so we can transform that score so we can compare it better to other scores. All right. So again, standardizing scores is one way to transform data. Transforming data allows you to change the units of measure to make comparisons easier. All right. For example, we can compare ACT and SAT test scores. Right? The SAT and ACT are both like college readiness assessments, so to say, right? We're much more familiar with the SAT out here on the West Coast, but like East Coast, Midwest, they tend to take the ACT a little bit more than we do. They're essentially the same type of exams. They're standardized tests to see if you are college ready, and it's one measure. However, the ACT is on, I think, you score somewhere between like 0 and 35 or something like that. And the SAT, I think now is out of 1600 again. I know for a while it was out of 2400. So the range of scores are vastly different between the two tests. But if I standardize those scores, I can compare the two results, right, by using that z-score. Now I'm comparing distances between kilometers and miles, right? I can adjust units, comparing grades from percentages and 4-point scales. Again, we can use this idea of transforming the data to compare things that don't easily compare otherwise because they're in different units or their ranges are really different, things like that. All right. So here's an example of transforming data here. We have students are asked to guess the width of their classroom to the nearest meter. Their guesses are displayed on the dot plot below. So we have our original data set here. The students in a class guess the length of the width of their room. And you can see there's quite the range of answers. We have our summary statistics down here. There are 45 students. We have our mean of 15.822, standard deviation, min, Q1, median, Q3, and maximum. All right. So we have this data here. And this is in meters. Okay. And then this next dot plot shows the amount of error in each student's guess. We have it compared to the original data set. The error was calculated by determining what the actual width of the room was, which was 13 meters, and subtracting that from the student's guess. So you had an error of 0 if you guessed correctly at 13. So with this calculation, it was possible to have negative numbers, because some people guessed too low, so their error was negative. They guessed far too low. And a positive number meant you guessed too high. So this is what our distribution looks like with the adjustment of subtracting the actual length from the student's guess. Right? What changed? If we compare these two dot plots, what changed and what stayed the same? Right, so let's just focus. What stayed the same? Yeah. All right. So Allison, yeah, saying the data just shifted to the left. Mm-hmm. So if it just shifted So let's think about our summary statistics, right? We have shape, center, spread as our main categories, right? Did the shape change or stay the same?
It stayed the same?
Yeah, the shape is exactly the same, right? We could overlay the two graphs on each other and they would match up still, right? So stay the same, we have the shape. Thinking about center, like mean and median, did those stay the same or did they change? So again, if we compare the two graphs, is the center, the value of the center, did it stay the same or did it change when we subtracted 13? This is easy. You said something stayed the same. What stayed the same? Okay, for the shape. Yeah. All right. So again, did the measures of center stay the same or did they change? And we're thinking of mean and median. Did those change or stay the same? They changed, right? We can see by looking at the graph that our center has moved. Yeah, it's not at the same number, exactly Caesar and Allison, they changed, right? So the center, that changed. And when we say center, we're thinking of mean and median. Okay, so the center changed. What about the spread? Did the value of the spread, like how spread out everything was, did that change? Like if we calculated the range, would it be different? That if we calculate the value of the range and the value of the IQR, is that going to be the same or different for these two graphs? Right, so Allison is saying the spread changed because the values the points are greater. Right? So it's true, the range itself, right, the values that everything falls between are different, right? They've all shifted. So remember, the range and the IQR, those are just numbers, right? Where I take, for the range, the minimum, or the maximum minus the minimum, right? So that would be 40 minus 8 for the guess in meters, right? 40 minus 8, which would be 32. And then we have 27 minus negative 5, which would also be 32. Right? So as far as the value of the range, right, it stayed the same. And the value of the IQR, these stay the same. And we can see that because the range for both is 32. And we would find the same thing as the value of the IQR would be the same. Now, the location, right, of these values have shifted, right? Those all changed, right? Our minimum, Q1, median, Q3, and max, those have all changed. They've all been shifted, right? So when I add or subtract a number, in this case we subtracted 13, the shape will remain the same, right? And the values of the range in IQR stay the same, right? But then we have the center and like location of data, those are going to shift. They're going to change. Okay. And to sum that up, we have this little thing here, effect of adding or subtracting a constant, adding the same positive number A or subtracting A from each observation adds that value to the measures of center and location, mean, median, quartiles, percentiles, but does not change the shape of the distribution or measures of spread, range, IQR, and standard deviation. So it changes measures of center and location. Or, I'm sorry, it changes measures of center and location. Right, it adds or subtracts based on what we're doing. Super dark. I don't want that color. Right? So we have the measures of center and location. Those will change. Will stay the same. I'm sorry, change. Bleh. I can't speak this morning. But shape and measures of spread will stay the same. Right, and that's for adding or subtracting a number from our data to our data set, essentially, right? If we shift things left or right. So next here, we have the same group of students are now converting their error data to feet. So instead of measuring their error in meters, which is our top graph here, we've now converted that to error in room width based in feet of length, which is a little more familiar to them. Here's their new data compared to the original data. All right, so again, we should see the shape is the same, right? Now to convert meters to feet, we have to multiply by a number. I forget exactly what that is, but it's a little over 3, I think. I don't remember. So they've multiplied all of their data points by this number, which is why we're looking at the effect of multiplying or dividing by a constant. And we see that the shape stayed the same. All right. What else stayed the same? Did anything else besides the shape stay the same? All right, so Allison, that's a good guess, right? Because it does look like the range is the same because the graphs look the same. However, you have to look at the numbers. Right? Our graph on the top here, when we're looking at meters, goes from that -5 to 27. Graph on the bottom here goes from -8 to 89, almost. Right? So the range, the size of the range has changed. It looks about the same, right? It does look the same, like size-wise. However, when we consider the numbers, we can see that it's not. Okay, so in short, the only thing that does not change is the shape when you multiply or divide by a number. All right, multiplying or dividing each observation by the same positive number b multiplies, divides the measures of center and location, right? Mean, median, quartiles, percentiles, right? So all of those are multiplied by the number, as well as the spread, right? Measures of spread will also be multiplied. The range, IQR, and standard deviation are all multiplied by that same number. So everything basically gets multiplied. The only thing that doesn't change is the shape. Right? So when multiplying or dividing by a constant, when you're transforming data, shape stays the same, everything else gets multiplied. All right. Last thing. Just a couple of quick examples on how to use this transformation of data. All right. So our first example here, we have Sam. He goes to a restaurant. He always tips the server $2 plus 10% of the cost. Sam's distribution of meal costs has a mean of $9, standard deviation of $3. What are the mean and standard deviation of the distribution of his tips? Okay, so we have our original mean and standard deviation of 9 and 3. Okay, so we need to figure out, based on his tipping practice of $2 plus 10%, what is that going to do to the mean and standard deviation? All right, so adding a number, right? In this case, we are adding $2 and we are multiplying by 0.10 for 10%. Okay? Order of operations says we're going to need to multiply first before adding. So the mean, all right, goes first because it's the first one listed. All right, so our new mean, if we're starting at 9, we multiply by 0.10, then we add 2, right, because we get 10% of the cost and then add $2 to that. That will be $2.90. So this will be the new, this is the mean for the tipping distribution. The standard deviation, remember, does not change when you add to it, when you add to a distribution. So with the standard deviation, I don't need to add the $2. The only thing that affects the standard deviation is multiplying. So for the standard deviation, all I do is multiply by the 10%. And that means we take our multiply by 0.10, and that will give us 30 cents. So Again, we did this based on those two lists of the properties, right? Adding and multiplying have an effect on the mean, right? They shift the value, right? Multiplying is the only thing that changes the value of a standard deviation, right? When I add, it's going to shift that data set, but the standard deviation is going to stay the same. So adding or subtracting doesn't change the value of a standard deviation. Only multiplying or dividing will. All right? So that's why we don't have to worry about that $2. So this is our, right, the tipping mean and our tipping standard deviation. Any questions on that problem? Okay. Then on the next problem, we have scores on the ACT college entrance exam follow a bell-shaped distribution with a mean of 18 and standard deviation 6. Wayne's standardized score on the ACT was a negative 0.5. What was Wayne's actual ACT score? So this is actually more like just solving an equation. We're reversing the transformation from the standardized score back to the actual score. Right, so we know we're going to use the formula, right? The z equals our x minus x bar over the standard deviation. I know what the value of z is. It's negative 0.5. I don't know the value of x. That's what I'm looking for. Minus the mean, I have that, divided by the standard deviation of 6. Right, so this is just about setting up the equation to work backwards. Right? So to reverse this, we first multiply by 6 on both sides. Right? That cancels the 6 that's being divided. 6 times negative 0.5 is negative 3. That's going to equal x minus 18. We add 18 to both sides. That 18 goes away. Negative 3 plus 18 equals 15. And that is the original score, his actual ACT score. Okay? Which kind of makes sense. If he's negative, he's half a standard deviation lower than the average. Half of 6 is 3. 18 minus 3, 15. Right, so these are just two examples of how we can use that kind of knowledge of transformation and how a transformation has occurred to find other values and say something else about our data.